Welcome to Complexity Made Simple, and also welcome to this video, which is now, of course, we're looking at the Catapult case study. We're now looking at video 3, and in video 3 what we're going to go into now is analyze and improve. Analyze and improve. Now you'll see when we do the analysis, these two come together. So define and measure come together, analyze and improve come together. Now this analysis is not mathematical analysis, it's process physics analysis. So let's get on. We're going to use a technique called process flow, cause and effect. The reason we're going to do this is because the process was chaotic. Our problem is variability, and because our problem is variability, we need to do a physics analysis. We use these tools for the physics analysis, and that's how you decide. Once you know the state of the problem, you know the tools to use to do the analysis. Let's take a look now. Okay. Welcome now to the process analysis part of the Catapult exercise. Now, what we are going to do is we are going to do some process analysis. We're going to do process analysis based on the fact that we have a very noisy process. So are we in chaos? Or are we in control? Well, we've just taken the data and we've seen a 43-inch range. We've seen a 43-inch range for our process. The process is in chaos. So the type of process analysis we need to do is based on that need. And what we're going to do is a technique called process flow, cause and effect. Okay, so process flow here, and then we're going to do cause and effect here. So the first thing we want to do is the process that we've just gone through in firing that catapult, right from the point where we did the setup to the point where we started producing. And the process flow will be a flow diagram of the production process. So let's just go through this. So process flow, first thing we did, so job one was to set the catapult up. So I put the catapult on the floor, I put the tape out, etc., and just got ready to fire the catapult. Now in this case, I've put setup in its own box, just one box, because the setup just takes a few minutes, maybe 30-40 seconds to do, and therefore it's easy to find the variables in such a short, simple step. But if the setup takes 3 hours, what would I do? I would actually do a box for each part of that setup in great detail. So I would break the setup down into just a few minutes worth of work, and therefore if it took 3 hours, I would probably have 30 or 40 boxes on my flow diagram. Okay, so this is simple because the setup is simple, but if it's complicated, do individual boxes. So the first thing we did, setup. Then what did I do? Came to the catapult, load the ball. All right, very straightforward. And again, the amount of information in this box is to do with the fact that the step is very quick. You don't want to say, make the component if making the component lasts an hour. This box here doesn't want to be an hour's worth of activity. It wants to be about 10-20 seconds worth of activity, maybe a minute's worth of activity, so that we can easily analyze each box. So load the ball. what would I have done next? Pull back. Okay, so pull the arm back. Maybe the next thing I do is I put my hand to steady the catapult. Okay, so I steady it. Then the next thing I should do is a decision. So what I should do, I should check. Am I at 177 degrees? That's a decision box. If the answer is yes, of course, I'm going to carry on and I'm going to fire the catapult. But if the answer is no, we're going to go back and slightly adjust the pullback. Alright, so am I at 177 degrees, which is the standard for the catapult. Then if the answer is yes, what am I going to do? Okay, so we're going to release the arm. We've got to spot where the ball lands. We've got to record that result. And what we've also got to do is return the ball. Okay. So there is the flow diagram of firing the catapult. So it's very simple, but it's very powerful, because what we're going to do now, we are going to visit every box, and at each box in the flow diagram we are going to ask ourselves, what are the variables, what's the difference that created our 43-inch range, and then we're going to use that difference to populate the cause and effect diagram. So we'll be doing that analysis next. Okay, so we're now going to do the cause and effect element of this analysis. So I've got the catapult with me, I've got the process with me just to help with this. Obviously, normally when you're doing this, you would have operators with you, people that have 5 years, 10 years experience of running this process, and they know everything that they've seen when they're running these steps. That's really important. The technical people don't really matter. I mean, the engineers kind of, yeah, okay, they might be useful for maintenance-y type problems, but really the operators are the people that are going to find all the variables that are causing this particular piece of chaos up here. Okay, so we've got the catapult with us anyway, just to help us. So let's get the cause and effect diagram drawn then, and then we'll show you how to fill this thing in. So six bones, I suppose, on your fish bone. The effect out here is the 43-inch. The 43-inch range. The headings, people, the machine, the method, the measurement, the environment, and the materials. Okay, so process, flow, cause and effect. So here we go. Look, first of all, we had to set up the catapult, and we had to set up a tape measure. So the setup is the first thing. So what are the variables at the setup? Well, let's have a think. The machine, how stable is it? Yeah, stability of the catapult. The tape measure, because Because if the tape measure gets moved, that's a variable. Now both of those were built in at the setup. It doesn't really matter where you find these variables, by the way, so there's no hard and fast way of doing it. If you're down here and somebody goes, hang on, I forgot one from up here, well, that's okay. Just put it on the cause and effect diagram. It's not a process that's got any rules to it. This is helping you simplify a complicated process, so you can easily think of all the variables in just this one step. So maybe there's only 5 or 10 variables in each box. That's how we're simplifying it. If there was 100 variables for your process and you tried to remember them all, you'd probably only get 80% of them. But if there's 10 here and 8 here and 3 there and 2 there, they're a lot easier to remember when there's small amounts of variables. That's why we use the flow diagram. So I've gone to the setup, stability of the catapult, stability of the tape. I'm going to say, normally there'd be a team of people doing this. Position of the team. Okay, so again, we decide that at the beginning. So the person who's going to spot where the ball lands, where do they stand, first of all? Well, they could be anywhere, couldn't they? And if they stand at 50 inches and the ball lands at 80 inches, there's a good chance they won't be able to read the tape correctly. So the position of the team is kind of important at the setup. Let's have a look. Anything else? Setup. I don't think so. Okay, loading the ball. So what's the variability of loading the ball? Well, one of the variables is how much force you put on this thing, because if you lean on this a little bit, the ball sticks in the cup. So under methods, load force. Now, just something to notice here. At no point am I being critical about anything. So I'm not saying we're using the wrong loading method. We don't know what loading method we're using. So how do we know whether we got the wrong one or not? So we're just saying we all do it different. We've all got different stability of tape, different stability of catapult. We're all standing in different places. Everybody's doing everything different, and if you do something different, you get a different result. If you do something the same, you will get the same result. So I'm not trying to assess each of these variables to say whether it's right or wrong. I'm just saying it's different, and the first thing we're going to do is we are going to fix all of these variables in one place. Then we'll decide whether they're in the best place. And we'll try and go for excellence after that. Chaos, control, excellence. Control is about fixing things. So we're not being critical of this. It's just load force. Okay, what else? What else at loading the ball? Well, one of the operators who's been on this catapult for 10 years, he's saying he doesn't think these balls are molded particularly evenly. So if you roll them on a table, you'll notice the way they rock backwards and forwards and settle into a position. So he's saying that the ball, the material, let's have a look, under materials. So I'm going to call this ball weight, because maybe on one side there is more weight than another one. Okay, so we've gone setup, we've gone load ball. Okay, pulling the arm back. So what are the variables of pulling the arm back? Well, it's all about what technique we're using. So different operators, some people are pinching it, some people are putting their finger on there, some people are grabbing the cup. Yeah, so at the pullback, we are going to put under method. What grip are we using? Okay, so that's the variable at the pullback. Is there anything else? The other thing that's happening, and again, this is a variable that an experienced operator has pointed out to me. If we hold the catapult in the down position, you know, just look, the pin the pin's rotating, and so the elastic is kind of changing in where all the force is. So under method, we're going to put down hold time. Okay, so we've gone setup, load ball, pull the arm back, then we say we're going to steady it, which of course is about the stability of the catapult and the tape. So let's have a look. We all might do this slightly differently. The steady, I'm just going to call it the steady technique. So again, I'm not saying anybody's got the right technique or the wrong technique. We are all doing it different, and there's the solution. The minute you see difference, that's your opportunity for improvement. Okay, so we got the steady technique, so we're down here. Then we've got the 177, so you know, the 177 angle. If what we're doing is we're simply doing it by eye, yeah, we're looking at this scale here, and then we're doing this, and maybe when we release it we pull it back and let it fly. So are we really at 177? Release it. Well, there'll be a release method. Okay, so the release method. What else we got? Then we've got spotting the ball. So I'm just going to put spotting technique for that one. Can we spot the ball? Then we record the results. Probably aren't any variables at recording the results. And finally, returning the ball. So the return method, maybe the return accuracy might be the one that we might write here. You can use different language obviously, but why is returning the ball part of this? Well, remember, this has to be conducted in a 15-second cycle. We have customers who want us to deliver every 15 seconds. And of course, if the 15 seconds is coming up to the end and we return the ball very badly, suddenly we're running out of time. What do we tend to do? We just throw the ball in the cup, fire it. The 177 goes all to hell in a handbasket. Yeah, so it puts pressure on the system if we get this wrong. So that's why we got that down as part of the variability. And I think that's probably all the variables that we're probably going to find and you know, think about it. It's a relatively simple process. We're just firing a catapult, and we've already found 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 variables. Plenty of opportunity to improve here, okay, because none of these variables are being controlled. They are all out of control. We didn't specify any rules about how to grip the catapult, how to steady the catapult. We haven't come up with a technique for spotting the ball, etc. When the ball's moving around by 43 inches, that's going to be pretty difficult to spot where's the ball going. So we've got lots of opportunity to improve, and this is process analysis in a chaotic situation. We are looking for difference. We fix the input difference, and what will happen if we fix the inputs? You'll fix the output. So now what we're going to do is we're going to look at a plan to control all these variables. Okay, what you can see us do now with all the information from the cause and effect diagram, we've taken this information and we've taken it onto a formal document. So I would always work like this with a group on a flip chart or a piece of paper or something like that, so that everybody can see the analysis. But once we've got the variables, we need to sit down and make a plan. So you can see, look, and you've got this in your notes, you've got the variable control plan. Obviously you've got an empty version of this, but I've populated the variables now into my variables control plan. So you can see now what we've got. We've got a list of variables. we've added a few more because whilst we've been thinking about this, the operator's come up with a few extra variables that we didn't capture during the original analysis. So let's just have a quick look through the list and the controls that we've agreed to use. So in no particular order, look, we've got the angle. Our control method is to put a solid stop at 177 degrees. To be able to spot the ball, the distance, we're going to put some aluminium foil down so that we can see where the ball hits the foil. It'll leave a mark. The tape location, well, we're going to tape it down, so we're going to use some packing tape, tape it to the floor. Stability of the catapult, the same thing, we're going to tape it down. Now the ball loading, we're going to come up with a standard operating procedure, so we're going to agree a method that everyone will work to. We've also come up with things like cup friction, so we've decided that although we've got a ball loading technique, maybe we should be careful with the friction between the ball and the cup, so we're going to put some talcum powder in there. We're going to come up with a standard operating procedure for the release method. The elastic tension, which is about how long we hold the catapult in position, what we're actually going to do is to put some sellotape around the pin and stop the pin from rotating. So that should eliminate the problem of how long do we hold the catapult down for. We've got a little bit of clutter in the area, so in order to get the place organized, we're going to use some 5S. The position of the ball, we're going to have a standard operating procedure. Now this is to do with the weight. So where we had the weight of the ball being different, that's what we mean by position of the ball. The returning of the ball, we're going to have a standard operating procedure. The elastic condition, well, we're going to have some planned maintenance because maybe over a couple of years, these elastic bands on the catapult, they do begin to deteriorate. So we're going to have some planned maintenance. And the operator positioning, well, again, we're going to have some 5S, we're going to have some workplace organization. So there are the variables, there are the solutions that we've come up with. And what we've also done is created some standard operating procedures. So you can now see all the elements that we've put in place. So you can see, look, we're showing you how to steady the catapult. We're showing you how to pinch the arm of the catapult. So that's the grip method that we're going to use. And we want you to align the ball. The arrow must line up with the little mark there, the green mark that we've created. So there's the firing SOP. You'll notice, by the way, in the top we've also indicated what quality of operator is allowed to do this technique. So this is a level 5 operator. There's the foil. You can see the mark on the foil. You can see the target that we're aiming for. And what we're saying is, please measure to the back of the dent that comes into the foil. Okay, you can just see at the bottom as well, look, you can see that we've indicated on the floor, we've done some workplace organization, we've labeled where the spotter will stand. They have to stand in the green square. We've got other areas, look, so that's the spotter, but we've got other positions. The operator has a position, the spotter has a position, the timekeeper, the returner. So we're laying the whole area out. You can see that the catapult has been taped to the floor. The other thing you can see, look, is that the firing standard operating procedure is at the point of activity. So this standard operating procedure here is at the point of activity. They can't miss this. It's in their eye line as they do the task. What else have we got here? And we've also indicated, now these variables were not on our cause and effect diagram because they weren't actually variables, but there is a standard way to set the catapult up. So we've indicated those settings with the green marks on the catapult. You can also see, look, there is a TPM maintenance sticker. It's telling you when the next date of replacing the Catapult elastic band is. So we've got all the variables now under control. So there are our variables and there are our solutions. Now they are the improve phase of this process. But what we've now got to do is we've got to talk about control. Now, real control happens over time. Control is something that happens over 3, 4, 5 years. It isn't something that happens instantaneously by the implementation of a solution, because what control is about is that actually you maintain those solutions over a long period of time. So now you can see the controlling process at the end of this plan. There is extra things in there. Now you will notice that in that column, they are the boring things that you hate. Things like doing ISO audits, 5S audits, TPM checks, startup checks, all of those types of things. They are boring checks and audits. But here's the point. You've got a machine that makes money. You have a problem. You've got this wild chaos. What you've then done is you've gone process flow, cause and effect. You've identified 15 things that are important to making money. You've identified ways of controlling them, and then you've attached the boring things to the money-making solutions. So these variables, these inputs that make money, are attached to the boring things so that they make money. ISO 9001, it is not to put a certificate on the wall. It is to make money, bucket loads of money. The only way you can do that is if you've done this analysis, you've used the principles that are in this exercise, and you attach your boring audits to your money-making solutions, and now your boring audits are there to help you make more cash. So that's what's in the controlling process column. These are the policemen that help you maintain control, and that's where real control sits. It sits over 4 or 5 years. It can't be done in the next 4 or 5 days. And that is process flow, cause and effect. That is how to remove chaos from your process. And by the way, the last thing to say, these solutions in a real situation will probably take you 3 months to implement. Okay, so this is not a quick 3-day thing. You can't fix chaos in 3 days. Normally there's lots of maintenance that you've been failing to do. It's going to take you a couple of months to get that maintenance back and in good shape. Then what that might mean is some of the other variables can't be controlled until you've done the maintenance. Then you're going to have to go and work on those. So 3-month time span to do this improvement work is the minimum. But hey, you've had this problem probably for 3 years. Surely you can wait another 3 months to solve the problem. Process flow, cause and effect, put all those actions into place, and now what we're going to do is fire the catapult again. Okay, well, we've fired the catapult again now, and as you can see, I put the results on the graph. I put them in a different color. This time we've got a range. Look at the consistency. Look at the range. It's just a range of 5 inches. We've taken all the chaos and variability out of this thing. We can now see, if you ask me, what target are you currently hitting? I mean, if you look at the black line, what target are you hitting? It's just all over the place. Now if you say, well, what target am I hitting? Well, I'm hitting 77 on the average. Now that I'm hitting 77 on the average, now that I can go and hit a target. So what we've done, look, is we brought the variability in so that it's like that. It's hitting a consistent place. And now what I can do is maybe make it and go and hit the place. Maybe we want to hit, I'd say we want to hit 89 as a target. Now we can easily make it hit 89 because I already know I'm at 77. I'll make some sensible engineering adjustments. We hit the target Now we have excellence. We had chaos, we have control, we have excellence. Hitting the target with 0 defects. Because what we did was, we had this problem initially. There is no point winding this thing backwards and forwards. There is no point twiddling on a setting, trying to make that result land on a target. What we've now done is that we haven't moved the middle at all. We don't need to move the middle at this stage. We need to squeeze the variability in. Process flow, cause and effect, standard operating procedures, and ISO audits have created that level of control, and now we're ready to make bucket loads of cash and have really boring days. Every day we come in, if we apply all the controls to this, we will do this. We will just get consistency. When you get consistent, it gets really boring and you make bucket loads of cash. Process flow, cause and effect, SOP, ISO 9001. Now that is a centerpiece of your project. 99% of the projects need this methodology. Okay, so there was the analyze and the improve phase, all in one step. So the design of those process controls, the reduction of the variability is designed to bring the randomness in, to make the process more predictable. And you saw that in the second firing of the Catapult when we used those techniques. So that was the improve phase. Now, before we go and do any more analysis on this process, the next 2 videos are all about important learning points from that exercise, and also some important advice about how to do process flow, cause and effect in a real environment, the sort of environment that you would have rather than on the Catapult itself. These videos come out once a week, so please subscribe and then you'll get a notification, and every week you'll get the latest Catapult case study.